Hi, this is John Whitaker, and this is our 11th lecture video for the probability graduate level class. And Travis, Wayne, today we're going to go over the CDF for a pair of jointly continuous random variables. And it's going to be using that old example we had before. And it's a complicated example, so it's going to take a little while for us to get through it. But let's start off with the example here. So we're going to let f of x comma y be defined to be equal to, it was 5/16 xy squared if you had 0 is less than x is less than y is less than 2, and it was 0 otherwise. B, the joint PDF of x and y, and the directions will be to find the joint CDF. And we're going to note that by f of a comma b of x and y. Okay, well, let us recall here this region for which the joint PDF is non-zero. Here, if we have 2, well, that's supposed to be a square. Y equal to x is here. It's this region here. And what I notice from the definition of this joint CDF, if, so this, I guess you could say case 1, if A is less than 0 or B is less than 0, then f of AB, which equals to the probability that x is less than or equal to A and y is less than or equal to B. Now, if either one of these is less than 0, well, then would you be integrating over that region, the joint PDF? Would you be integrating in the joint PDF would be 0. And so this is equal to 0. That's case 1. Really, I'm going to work on A more than I am anything. And so for case 2, if A is sandwiched in between, let's say 0 is less than or equal to A is less than 2, this one, then we'll talk about what B can be. But we know if B is less than 0, we get 0 for the joint CDF. So let's talk about B being bigger than 0. And so we'll have subcase 1. Here, that is, B is bigger than 0. It turns out a case to look at is that it's less than or equal to A. Here I'll just say less than A. And in this particular subcase, here's 2, here's 2. We're looking at this square. What I've got is A is somewhere here, let's say. Okay. So this is A. And what I want to look at is the case where B is less than A. That would be something like this. So this could be a B. I'm talking about this region, this type of region, is what we're integrating over. And so when I look at what f of AB would be, I would be integrating the joint PDF over this region. So here, we know it's 5/16 xy squared. And what I'm going to do is I'm going to rewrite this. I need to figure out what's happening here. So here, I'm going to rewrite this as dx dy. And the y values run from 0 to b. And for a fixed y value, the x values would run from 0 to this line. So that's 0. And that line is x equal to y, so I'll write down y here. Okay. So that's what I need to integrate to find the answer. All right, that's correct. And then let's compute this. So here we do the integration with respect to x first. So 0 to b is left there. The integration with respect to x would be 5/16 is a constant. Y squared is a constant. I'm just going to write here. The antiderivative of x is x squared over 2. I need to evaluate that from its x goes from 0 to y, dy. Now that's equal to integral from 0 to d. We'll let x be equal to y. This will become 5 over 32, 16 times 2. Here's the y squared times y squared, that's y to the 4th, dy. This is going to be 5 over 32, it's antiderivative, y to the 5th over 5, evaluate from 0 to d. The 5's cancel each other out. I'm left with b to the 5th over 5. That's what I get in this case. Now, subcase 2, we'll write over here. Remember, we're working with 0 being less than a being less than 2. So subcase 2 has to do with, now we're talking about b, what if a is less than or equal to b is less than 2? Okay. So here in this situation, I'll picture something like this. So this is 2, this is 2, this square. Here's a, okay. And b is up here. So we're looking at integrating to this region. And the way I think it's better to do that is integrate dy then dx, okay? So here, I'm going to rewrite dy then dx. So in this case, f of a, b. We want to integrate over this region, okay? The PDF again, don't forget, 5/16 xy squared. So when I look at this region, the x values definitely run from 0 to a. And a y value for each one of these fixed x. So if I fix x, now we're fixed in one of the x's, the y's run from this line, which is y equal to x, so x, up to the high values b. So now we need to do the same. 0 to a. Here, I'm integrating with respect to y, so it's 5/16 x is a constant. The antiderivative for y squared is y to the 3rd. Yeah, 1 to the power of y back to the power of 3. I evaluate this from x to b, dx. Okay. Stick in b. Integral from 0 to a. This will be 5 over 48. These are for y values. I will have b to the 3rd x, and then minus what I get when I let y be equal to x. That's 5 over 48, 16. This will be x to the 4th, dx. That's equal to, okay, so 5 over 48 is a constant. B to the 3rd is a constant. It would be x squared over 2 is the antiderivative for x. Evaluate from 0 to a, minus 5 over 48, x to the 5th over 5 is the antiderivative for x to the 4th. Evaluate from 0 to a. When I let x be equal to a, I'm going to get 5 over 40 over 96. This will be a squared b to the 3rd minus, this will be 5 over 48. Now, the 5's will cancel. So the 1 over 48, and then it would be a to the 5th. Notice when you stick in 0 for x and 0 for x here, you get 0, so there's nothing being subtracted from each one of these terms. Let me make sure I didn't make a mistake. That is correct. The next subcase, and last one for this that we're going to look at in this case, that's when B is bigger than or equal to 2. And so our picture, okay, so B is bigger than or equal to, A is something in here, we're looking like this. Something like this region is what we're trying to integrate f of x comma y over. But this region, f of x comma y, is equal to 0. So really, it's just this region here. This region is what I meant to over. And so what that's equal to is, again, the PDF, the joint PDF where it's non-zero, 5/16 x y squared, let's see, I think I'm going to write down dy dx again. And the dx goes from, x goes from 0 to a. And over this region, for any fixed x, the y value will go from y equal to x, that line, up to 2. For we don't need to go any further up here, because we do this, what we'd be integrating would be 0, not this particular function. So let's see what this is. So 0 to a, I differentiate with respect to y. This is going to be 5 over 48, x, y to the third. We did that just a few seconds ago. X to the 2. When I stick in dx, when I stick in 2, this is going to be 40 over 48. You know, this is 8. Okay, I'm letting y be equal to x and y be equal to 2. This is 8. 8 goes into 48. It's 5, 6. Let's write it down that way. X. So 5, 6, x. And then minus, when I let the y be equal to x, we get 5 over 48, x to the 4. And don't forget, we're integrating this from 0 to a dx. That's equal to, this will be 512 x squared minus, here it would be 5 over 48 times x to the 5th over 5, so it's 1 over 48, x to the 5th. I need to evaluate that from 0 to a. And when I do, we get 5 12 a squared minus a to the 5th over 48. That's what we get. Okay. So that takes care of that case. Case 2, I guess this is case 3. So case 3, the case that we just did based on A, was we did A is between 0 and 2. Well, what if A is greater than 2? So then we're going to have subcases on B again. So subcase 1 has to do with B being between zero, I think there's just going to be 2 subcases here. So here, 0 and 2. And here, if we look at our picture again, of where we're integrating, where the joint PDF non-zero. Okay, so here A is bigger than 2, something like here's A, and B is somewhere here. So really, the region that we're looking at, so this is what we're looking at. We're looking at the probability that X and Y are in this region. That's what we're doing, okay? That's what we're looking at. Because this is f of AB in this case is equal to the probability X is less than or equal to A. That's from here, and Y is less than or equal to B. So that's here, and the part of it that intersects with this, that's just this part. But the only spot over that region where the joint PDF is non-zero is over this region right here. This is B. Okay, so here we have 5 over 16 is the non-zero part of little f of x comma y, xy squared. Okay. So here's what I'm thinking. I'm thinking we're going to do it dx dy. And so the y values, okay, the y values run from 0 to b. But the x values for any fixed y will run from, well, so here's a fixed y in that region. The x values run from this line to that line. This line is x equal to 0, so that's why I put a 0 here. This line is x equal to y, so I put y. And then we figure out what this is. So I'm doing it with respect to x first, inner integral. Here, this integral, antiderivative with respect to x, is going to be 5 over 32. Just a little quick here. 5 over 32 be y squared x squared. So it's x squared over 2 was the antiderivative. That's having the 2 at the bottom. The 16 made 32. Here I evaluate from 0 to y. And once I get an answer for that, I'm going to integrate with respect to y. That's an integral from 0 to b. Here, when I let, remember these are x values. When I let x be y, I'm going to get 5 over 32 y to the 4, y squared times y squared is y to the 4. When I stick in 0, I get nothing. So just this, dy, and that is the integral of antiderivative for that is 1 over 32 y to the 5th. Stick in 0 to b, I get b to the 5th over 32. And then the last subcase is where b is bigger. Subcase 2. Is where b is bigger than or equal to. So here, this makes 2, this makes 2. Looking at the square, here's where, whoops, where f of x comma y PDF is non-zero is here. What we're thinking is a is here, b is up here maybe. And so what we're looking for is what's this chance happening. And you can see that means that we're just integrating this whole region, because over these regions we get nothing. So here this would be from, it would be integrating this whole spot here. So let's say the y is going from 0 to 2. Now I'm just integrating over this spot. The y's will run from 0 to 2. For a fixed y, the x's will run from 0 to x equal to y. 5 over 16 xy squared dx dy. That's my answer. I already know the answer's got to be 1 here. And so this is what f of AB is. This is equal to, well, it's integral from 0 to 2. I integrate with respect to x, so this is the 5 over 32, x squared y squared, evaluate from 0 to y, dx, which is going to be equal to the integral from 0 to 2 of 5 over 32. Here I let x be y, and I'm going to get y to the 4th. when I let x be 0, this part's going to be 0, so subtract 0 from that. Just lose this. dx, I'm sorry, this was wrong. This should have been dy. Now when I integrate with respect to y, I'm going to get 1 over, I'm sorry, I'm going to get 5 over 32, y to the 5th over 5, value from 0 to 2. Of course, the 5's cancel, we'll let y be equal to 2. 2 to the 5th is 32, so we just get 1 and we'll subtract 0. Okay. So it's a summary. Here's what we have for f of a, b. So it's equal to 0 if a is less than 0 or if b is less than 0. It's b to the 5th over 32 if 0 is less than or equal to a, is less than 2, and 0 is less than or equal to b is less than a. It was 5 over 96, I think we found. B cubed a squared minus a to the 5th over, I think it was 48. And that was if 0 is less than or equal to a is less than 2, and here I think we had a is less than b is less than 2. And then the third subcase in this output was, I think we had 5/12 a squared minus a to the 5th over 48. Okay. And that was when if 0 is less than or equal to a is less than 2, and here we had b was greater than or equal to 2. And then we had, it was b to the 5th over 32 if a was greater than or equal to 2, and here b was sandwiched in between. I think it was 0, 2, and then finally we get 1 if a was greater than or equal to 2 and b was greater than or equal to 2. So it's a lot of work, it's kind of complicated. I think it would be hard for me to give you a test question with this, but homework questions is okay. Based on this example, I think it's okay for the homework questions like that. Well, let's move on about some facts involving the joint CDF. The first fact I'm giving is something that's very easy to see and prove, and here's the fact. It says if f of a to b is the joint CDF of x and y, then we can find the joint CDF, I'm not the joint, but then the CDF of, so here's part 1, x is f sub x of a, which is equal to f of a comma infinity. And 2, y, part 2, y is f sub y of b equal to the joint CDF evaluated from infinity to b. And I'll do both of these, and they're very easy. So here's the proof. Analogous, and I'll do both of them. We're going to let f of ab be the joint CDF of X and Y. Okay. Note f of A, f of X and Y. All right, what is this? This is the probability that X is less than or equal to. That's its definition. Which is really the same thing, probability that X is less than or equal to A. And Y is, well, is less than or equal to infinity. Well, it's a real number. And so that's equal to f of A infinity using the joint CDF. Okay, the same thing happens for part 2, but I'm going to do it, even though it's repetitive. So for part 2, it's proved here, f sub y of b, that's equal to the probability that y is less than or equal to b, and that's equal to the probability that x is less than or equal to infinity, and y is less than or equal to b. But it doesn't matter what x is, just y's got to be less than b, but that's f of infinity b. So that ends that proof. Okay, the next thing I'm going to show has to do with the CDF where x and y are jointly continuous. So it's a fact. I'm going to let x and y be jointly continuous. Let, I'll just say then, in terms of notation, the second partial derivative, so if you take the derivative, second partial, respect to A, then, respect to B, then A, of f of AB, that's going to be equal to, that's the joint CDF. What you're going to get out is the joint PDF. Okay, let's prove this. Let x and y be jointly continuous. With joint CDF f of AB and joint, so this is my notation, okay? Joint PDF little f of x comma y. Okay. All right, now, here's what I'm looking at. I'm looking at this partial derivative, two partial derivatives acting on f of AB. Well, that's the partial derivatives acting on the quantity. So here, the integral from minus infinity to b, by definition of this. Integral from minus infinity to a of f of x comma y, and then this is dx dy. Where this means we take the partial with respect to a after we take the partial with respect to b of this double integral. Then I believe I'm going to switch the order of integration. I'll rewrite this with minus infinity to A, minus infinity to B, f of x comma y, dy dx. And then here, we can bring this derivative inside this first integral, because it's with respect to x, it doesn't have a b in it. And so here, it's partial with respect to A. Here, integral from minus infinity to A, partial with respect to B. Switch the order of these limits, if you will. Here, this is going to be the integral from minus infinity to B of f of x comma y dy. We're going to do that first. And then dx second. From where we are, we think of, in this case, because we're integrating with respect to x, with respect to y, x is a constant, okay? X is a constant, this is all in terms of y. So here, this is, we can use the fundamental theorem of calculus. And what we get, it's the second part of the fundamental theorem of calculus. What we get is this is equal to the partial with respect to A. Here is an integral from minus infinity to A. Here, by the fundamental theorem of calculus, that next part is nothing more than f of x b then dx. So that inner integral's derivative just becomes the partial, the joint PDF evaluated xb. And now, again, using the fundamental theorem of calculus, this ends up being where b is a constant. This is f of a, b, and that's what we're trying to prove. So that ends this theorem's, or this fact's proof. Well, we had the expected value for a function of a random variable x, and now we're going to have the expected value of a function of two random variables. We'll say we know how they're jointly distributed. So as a definition, let x and y be random variables. And g of x comma y be a function of x and y. Then the expected value of g of x comma y is denoted by the expected value of g of x comma y, and given by, I need to look at that right. So we have two cases that we'll look at. Our two cases are both of them discrete continuous. So here's, it is the expected value of g of x comma y equals, well, here are the two situations. It's the sum over all x's, sum over all y's of g of x comma y, f of x comma y. And this is if x, y are discrete. Here, it's the integral from minus infinity to infinity, minus infinity to infinity, of g of x comma y, f of x comma y, if x, y are continuous. So that's what we're finding, those two situations. And we're going to do two examples next. It's we're going to have g of x be the same function here, but our examples are let, oh, I should say something, where f of x comma y is joint, and I'll say p m f in case 1, and f of x comma y is joint p d f in case 2. 1, 2. Okay, that's what we do. So the discrete case example, the one we've seen before. We're going to let f of x comma y be equal to, I think it's that x plus y over 21, if x equals to 1, 2, and y equals to 1, 2, or 3. And that's going to be the joint PMF of x and y. So here's what we're going to be asked to find. We're going to find the expected value, let's see, of x squared times y. X squared times y. Okay, that's fine. Okay, note the expected value of x squared times y. This is easy. This is equal to the sum over all x's. Well, what's x? It runs from 1 to 2. Sum over all y's, that runs from 1 to 3. Here it's going to be x squared y, and then times x plus y over 21. Okay, so I have 6 things to add up here. So let's see what the first one is when x is 1 and y is 1. So I'm going to get 1 squared times 1, and then 1 plus 1 is 2, so it's 2 over 21. Plus, when x is 1 and y is 2, I'm going to get 1 squared times 2, and then here this is 3 over 21, plus, when x is 1 and y is 3, I'm going to get 1 squared times 3 times 4 over 21, plus, now when x is 2, I'm going to do this a little faster. This is 4 times 1, and then this is going to be 3 over 21. Plus, here when x is 2 and y is 2, I'm going to get 4, I'm going to get 8. And then this is going to be, remember 2 and 2, this is 4 over 21. And then finally, when x is 2 and y is 3, this is going to be 12. And here, we're going to have 5 over 21. So when I add these up, let's see. This is 2 over 21. This is 6 over 21. This is 12 over 21, I think. This is going to be 12 over 21. This next one is 32 over 21. And the last one is 60 over 21. Okay. 92, 94, 104, 106, 116, 116, 122. I'll get 124. Over 21. I'm not going to reduce that. There it is. We'll do a similar problem. As an example of what we've had, we're going to let f of x comma y be equal to, okay, this was 5/16 xy squared if 0 is less than x is less than y is less than 2, and 0 otherwise. B, the joint PDF of x and y. Find the expected value of x times y squared. So in this case, this is equal to the integral minus infinity to infinity, minus infinity to infinity, of g of x comma y, f of x comma y, dx dy. Well, look, f of x comma y a lot of times 0. The only time it's not 0 in this region. You've been working with this a good bit. So it's this region. So what is this? Let's see. Well, I'm going to integrate again. Let's see, what do the y values run from? They run from 0 to 2. And for each fixed y value, the x values run from 0 to x equal to y. All right. And then g of x is x y squared. That's what I could do. No, I'm going to change this. X squared y. Same thing we had. Okay? X squared y. It's the same problem we had. Okay? Here, this is going to be 5/16. Just wanted to change it because I already had done the problem, so I know what the answer is. Dx dy. All right, look. Let's finish it up over here. Okay. All right, so this is equal to, okay, so when I look back over here, it's integral from 0 to 2, 0 to y, and then when I simplify this, it's 5/16. It's x to the third, y to the third, dx dy, that's what I see. And then, so we integrate with respect to x first. And this would be 5/16, x to the 4th over 4, y to the 3rd, I'm sticking 0 and y for x's. And then dy, this is equal to, so 16 times 4 is 64. So then it'll go from 0 to 2, this is 5/64. I'm going to let x be y, so this is going to be y to the 7th, that's what I see. That's what we have, and when I stick a 0, I get nothing. Dy. This integral from 0 to 2 of 5/64, y to the 8 over 8, value from 0 to 2. When I stick in 2, well, this is 5/64. This will be y to the, well, so I have 8 here in the bottom, but this would be 2 to the 5th here, okay? Because the 2 to the 8 is 2 to the 3rd times 2 to the 5th. 2 to the 3rd is 8, goes to cancel, so I just put out 2 to the 5th. That's 32, I get 5 back. And that is the answer that I have on my sheet, so that's good. Okay, so that is that problem. I'd like to do one more fact, and then cover one more concept having to do with independence of two random variables. Okay, so as a fact, the expected value of x plus y is equal to the expected value of x plus the expected value of y. And this is where x, y are either both discrete or both continuous. And so here's the proof. Well, note, so proof. Case 1, x and y are discrete. So if they're both discrete, then the expected value of x plus y, by our definition, is the sum over all the x's, sum over all the y's, of x plus y times f of x y. Okay. This is equal to the sum over all x's, sums over all y's. If I distribute that joint PMF, I get f of x comma y plus y times f of x comma y, which I'll rewrite as two double sums. So it's the sum over the x's, sums over the y's of f of x comma y, plus sum over the x's, sum over the y's of y times f of x comma y. From where we were, in the first double sum, it can be pulled out. In the second sum, I'm going to change the order of summation. So here, I'm going to have y f of x comma y. Here, this is equal to the x's, the sum of the x's of x, but here, this is nothing more from a previous definition of f of x of y. That is the PMF of x, I should have x, plus, here, this is sum of y, I pull y's out, sum of x, f of x comma y. This is equal to the expected value of x, that's exactly its definition, plus this is the sum over y's. Here, this is the, I should say PMF, I don't know what I said here. It's PMF of y with respect to y, and so that's the expected value of x plus the expected value of y. There's a little bit of worry about being able to switch the order of these summations, but I'm just going to say that we can do it. Okay, that's all I'm saying. And in case 2, for case 2, here, the expected value of x plus, what is case 2? X and y are continuous. So the expected value of x plus y, this works analogously except with intervals, what I just did. What is this? This is the interval minus infinity to infinity, minus infinity to infinity, of x plus y times the joint PDF f of x comma y dx dy. that's equal to, I'm going to skip a little bit, to 2 double intervals. Here it's going to be f of x comma 1 dx dy plus double interval from minus infinity to infinity, minus infinity to infinity. Here's y f of x comma 1 dx dy. This is equal to the interval from minus infinity to infinity. I can pull out, well, I'm going to switch the order of integration. Minus infinity to infinity. We'll write down x f of x comma y dy dx. Again, I can do that, but I'm not going through the details why I can switch the order of integration. Here, I can pull out a y because of inner integrals with respect to x. And this minus infinity, whoa, this is a y here. Minus infinity to infinity is f of x comma 1 dx, this dy. This is equal to, now I can pull out the x from this integral from minus infinity to infinity, f of x comma 1 dy dx, plus here minus infinity to infinity, y. Now, the integral with respect to x from minus infinity to infinity of the joint PDF, that's just equal to the PDF of y. Similarly, this is the integral from minus infinity to infinity. This is the joint PDF of x, so it's x times f of x, not the joint, but the PDF of x dx plus what this guy is nothing more than the expected value of y, which equals the first one. The first integral is the expected value of x plus the expected value of y, and so that's the. Okay. Last topic. We'll give 2 definitions for it and then prove 1 fact, and that'll be it today. So we want to talk about 2 random variables being independent, so we would say. Two random variables are said, 2 random variables, let's call them something, x and y, are said to be independent if for all A, B being subsets of R, the probability that x is an element of A and y is an element of B is equal to the probability that x is an element of A times the probability that x is an element of B. That's what it means to be independent for both continuous and discrete. So here's an alternative definition. So these are equivalent definitions. I'm not going to prove this. I'm just saying it's another definition. X, 2 random variables are independent. Let's give them names. Again. X and Y, sorry. If f of AB is equal to f sub x of A times f sub y of B, where these are CDFs. Joint CDF, CDF of x, CDF of y. They're the same. These definitions mean the same. Okay, the last thing we're going to do is prove it on fact. It's an if and only if statement, so we're going to have to prove it both directions. Here's what it says. It says X and Y are independent. Okay? If and only the joint PDF or PMF between f of x and y is equal to the multiplication between the PMF or PDFs. So here is the proof. So here we're thinking that x and y are both discrete or both continuous, okay? So here, f of case 1, first of all, I'll go in this direction. What's this direction? Assume or let x and y be independent. Consider two cases. Case 1, x and y are discrete. All right, then if x and y are discrete, we want to prove this, okay? Show this. Well, f of x comma y is equal to the probability that x is equal to x and y is equal to y. That's the same thing as the probability that x, if you will, belongs to the set containing little x, and y belongs to the set containing little y. Okay? By the definition of independence that I first wrote, this is equal to the probability that x is an element of x, the set containing x, times the probability that y is an element of the set containing little y. And this is nothing more than the probability that x is equal to x times the probability that y is equal to y, and that's equal to f of x times f of y of y. So we've proven it when we're having discrete random variables in this direction. Case 2, x and y are both continuous. Then, so in this case, we're assuming, since x and y are independent by the alternative definition, that means that f of AB is equal to f of x of A times f of y of B. These are CDS. Okay. Now, we use that fact about the partial derivatives. So, note, partial derivative with respect to A and B, f of AB, that's equal to little f of AB. Also, the second partial, the partial with respect to A and B, of f of x of A times f of y of B. Now, if this is going to be equal to partial with respect to A and partial with respect to B, so the quantity f x of A times f of B first. This doesn't have a B in it. So that's equal to the partial with respect to A. It's a constant. We can just write it down. And now the partial of this guy is nothing more we've proven already, that it's f sub y of b. And that's equal to, well, this is a constant, so I can pull it out, x y b, times partial with respect to a of CDF of x of a. That's nothing more than, this I should pull it out, equals little f. I didn't draw this very well. It's little f. Little f. Here's little f of sub x of a, because of the previous factor we proved. So that's what we have. That proves it in this direction. Even though I've got it written in terms of A and B, you can substitute x and y for those variables. That's what you get. So that's one direction. Okay, in this direction, we assume little f of xy is equal to f of x of x times f of y of y. We must show x and y are independent. So we have two cases. Case one, x and y are discrete. Okay, so in this case, here what we examine is that f of AB, so to show independence, what we're going to show is f of AB is equal to f sub x of A times f sub y. So here, independence, this is equal to, we're discrete, so this is sums over x's less than or equal to A, sums over y's less than or equal to B, of f of x times y. And what we do is we substitute what we're assuming here. This is sum over all x's less than or equal to A, sum over y's less than B. Here, we can rewrite this f sub x of x, f sub y of y. So this guy didn't have a y in it, okay? So I can pull it out as a constant. So this is the sum, x less than or equal to A, f sub x of x, times the sum, as y is less than or equal to B, of f sub y of y, and that's equal to, this first sum is nothing more than f sub x of A, that's its definition, times f sub y of B, where these are big F's, they're CDFs. And that proves this case. Okay? So the joint CDF is equal to the multiplication of each individual CDF. That shows the x and y. We only got one more case to do. Here's the way I'll show it. Maybe not the only way we can show this. So lastly, case 2. X and y are continuous. Then here, the probability that x is an element of A and y is an element of B. So I'm using that first definition to try to prove independence. That's going to be equal to the interval over b, interval over a, of f of x comma y, dx dy. Now what we're assuming is that this joint PDF is equal to the multiplication of each individual PDF. So this interval from b over b, I should say, over a of f sub x of x times f sub y of y, dx dy. Now, the first interval has to do with x. There's no x in here. I pull it out. Interval over a, f sub x of x. And then this is dx. We'll do this first. Y. And so when I do that inner interval, that's the interval over b, f sub y of y. And what is that interval? Well, if you will, you can pull even that interval. It's a constant. It's a number. It's the probability. X is an element of A. It's a constant. Okay? Times dy. And so it's a constant. So I'll pull it out. It's the probability X is an element of A. Times the integral over b of f sub y dy. And that's equal to the probability X is in A times this last interval is the probability y is in B. Because that's what the PDF does for random variable. It's the thing that you integrate to find the probability that y is over, it's in the interval, in the region that you're integrating over. So, thus, x and y are independent. Okay, stop there. That's the proof. Thank you very much for your time and patience.